I've collected hundreds of littered disposable vapes, and I'm going to use them to power this e-bike.
Oh Christ.
So in the last video we found out that these disposable vapes have fully rechargeable lithium-ion cells in them, and that let us build these massive power banks. And it really got me thinking, why can't we just dial this up to 11 and power light electric vehicles from them? At the end of the day, a battery is a battery, and with enough of them you can pretty much power anything. Now I think this is going to be especially interesting because the battery of an e-bike is the most expensive part, and we're getting all these lithium cells for free. So not only could I possibly be helping the planet a bit, but I could also be saving a bunch of money in the process. To quickly recap just how bad the disposable vape industry is, we throw away 260 million of these per year just in the UK, and that's enough lithium to make 1.3 million e-bike batteries and 49 million mobile phone batteries. So I guess let's do our part by raising some awareness about this and also making some cool stuff at the same time.
A quick disclaimer before we start: I don't endorse or encourage vaping, and all material here is for entertainment purposes only. Lithium batteries are extremely dangerous when improperly handled and can result in fires and explosions, and as we are handling used, discarded vapes, they should actually be treated as a biohazard. This video is not a guide, and you should not attempt any of the following unless you're a professional and acting at your own risk. If we're going to make an e-bike battery, first we need to understand how one's made, and if we crack one open, we can see that it's made of lots of small lithium cells called 18650s. These particular cells are used everywhere, from some electric vehicles to laptop batteries. The construction is actually really similar to the power bank we made last time. These cells are grouped in parallel to add up all their capacities, in which an individual group is about 3.6 volts. So to make a 36 volt battery, we stack 10 of these in series, and to make a 48 volt battery, we stack 13 of these in series. So the manufacturers just arrange and connect together all the cells to get the battery specs that they want. But we're not finished yet though. We need a component called a battery management system, or BMS. This constantly monitors all of the cell groups to make sure that they're all operating safely. Therefore it has wires connecting it to each cell group so they can read all of the individual group voltages and keep them all in a safe range. Sadly, a lot of the dodgy batteries that keep exploding have likely skipped out on adding a BMS just to keep the cost down. But that's pretty much all there is to it. So we're going to do exactly the same, except we're going to use vape cells instead of 18650s. So I'm going to make groups of 10 cells so it's nice and high capacity, and then we connect together 13 of these groups in series for 48 volts. But that means that we're going to need 130 vape cells. Good thing I've got an ammo container full of 150 of the larger vapes. Now technically we could use the more common smaller vape cells, but we'd need almost 400 of these because the bigger one is triple the capacity of these smaller cells. I found that the easiest way to crack these larger ones open is to clamp the bottom in a vise, rip it off, and then just pull all the bits out. Now don't ask me why the liquid sponge is this colour inside this one. It should actually look like this, so God knows what some people are breathing in. Then we can remove the insulating tape and desolder the cell from the rest of the parts. Quick side note, look how much fluid is still left in a supposedly empty vape. If the manufacturers let you recharge it, then it'll easily last 3 or 4 times as long as it currently does. How wasteful is that? This stuff can also be absorbed through your skin and can be pretty dangerous in these quantities, so gloves are definitely essential. Compared to the power bank we built, I'm planning on drawing a hell of a lot more power from the cells this time, so I need to find out exactly what they're capable of, and that means getting my hands on their datasheet. But this data is pretty much impossible to find, so I decided to hunt down the actual suppliers of the cells, and I asked them for the datasheet, and they actually sent it over. Here we go. These larger cells are rated for 300 full recharge cycles and can do 3 amps of continuous current. I'm not going to bore you with all the maths here, but that means we can deliver 30 amps from this battery, and at 48 volts that's almost 1500 watts, which is a hell of a lot of power for an e-bike, especially when you consider that the legal power limit in Europe is only 250 watts. So I expect this e-bike to be propelled at 35 miles an hour with this battery pack we're making. I want to check the quality of these cells for myself, because you'd assume they'll be pretty bad if they're only intending them to be used once. So I went ahead and bought this cell tester, and I've added on some crocodile clips so we can hook up the vape batteries. Supposedly these cells are meant to be 1500 mAh, which is about half the capacity of an iPhone 16. So let's see what their real capacity is. Oh right, so they are actually 1500 mAh. We can also measure what's called the internal resistance, and it basically just tells us how well the cell can deliver power. It's this yellow number here, and that's a pretty good value for some free cells. So with all that out of the way, let's get ourselves 130 cells harvested.
Slowly getting there. Still got quite a few to go though. Wow, now this is a serious amount of cells. And it turns out that the casing is actually
aluminium. So we can separate out the plastic and get these recycled. Now for the long process of removing all the other parts from the batteries. While I do this, I'm going to talk about this video sponsor, JLC PCB. My place is quite literally overflowing with custom PCBs for all the various projects that I've been working on over the last 5 years. And JLC has always been my go-to manufacturer because of how low cost and high quality their services are. Getting 5 PCBs made can be as little as $2. So at these costs, I don't even bother with breadboarding prototype designs anymore and all the headaches that come with debugging these. I'll just order a cheap PCB, and as long as your design's good, it's going to work every time. Their PCB assembly is great and really cheap too. It's allowed me to create all sorts of products, from fighting robot control boards to motor controllers for my 45-mile-an-hour mobility scooter. Without accessibility to these services as a hobbyist, there's absolutely no way I'd be making the things I am today. They also do CNC machining and 3D printing, which I'm going to be using for the case of this e-bike battery, so definitely check them out using the link in the description. Now back to the build. Well, that took absolutely ages, but that should be all of them. And the smell coming off this stuff is pretty overpowering, to be honest. You'll remember from the last video that we had to make sure that the cells are all the same voltage before connecting them together in parallel. Otherwise they'll try and charge each other super fast and things can get pretty spicy. And last time I used a PCB with resistors to let them charge each other slowly. But this time I'm actually going to use the cell tester to charge up all of the batteries individually, all to the exact same voltage, which is the more common approach that battery builders use. Here we go, the cells are now approximately the same voltage, and their internal resistances are looking pretty good. Except for this one, 75 milliamps is quite a bit higher than most of the others. This isn't too much of a big deal though. What I'll do is I'll just make a note of its resistance, and then I'll group it with other cells that also don't have a great resistance. This will pretty much just ensure that all the cells will do the same amount of heavy lifting when they're paired up with each other. And sadly there's some cells that are just completely dead. You see, lithium-ion cells degrade when they're discharged below 3 volts, and this one here is 0.7. So yeah, straight to the bin for this guy. Finally, 130 of them extracted, balanced and grouped. To hold these together, we're going to be using a bunch of 3D printed modules. Each module can hold 10 cells, so these will form our parallel groups. We've gone for the nice spring tab design again, and trust me, this is needed. I mean, look how much the dimensions can vary between these. These modules can also slot together, which will help us make a solid pack. So let's get a bunch more of these printed. Making one of these modules is pretty easy. We've just got to slot in all the cells, pull all these tabs into the centre, solder them all up to a copper strip, flip it over, and then repeat again for the negative side. And then we repeat this 12 more times. This is the arrangement I'm thinking for the final assembly. So we still need to connect all of these up in series, and that involves us connecting the positives to negatives, the positives to negatives, and that's how we stack them all up in series. And that's why I've been reversing the orientation of each cell groups, because it's going to make the wiring so much easier. I can just put a connection here, and there we go, positives to negatives, flip it upside down, now the next one, positive to negative, and I just keep repeating that process until we will have stacked all of these up in series. I'll do the same thing for this lot, plonk it on top, and we should have our 48 volt battery that's also pretty darn high capacity because we've got so many of these in parallel for each group. So you'll have noticed as I've been building this pack, I've been putting on this insulation tape all over the copper bus bars, and there is a really good reason for that. That's because building lithium-ion battery packs is really bloody dangerous. So let me show you this module, which has got 2 of them connected together, and if I was to accidentally drop a piece of metal that joined these 2, we're going to form a complete short circuit, and realistically something is going to set on fire or explode. So I'm actually going to show you guys what happens in the event of a short circuit in hopefully a controlled way, all in the name of science. First I'm going to put some heat resistant tape on. Alright, here goes nothing. Oh Christ. Yeah, look at that.
So definitely don't mess around with lithium-ion batteries. Time for the moment of truth. Now, if we measure the voltage across the negative and positive of our battery, we should see around 46 to 48 volts. Look at that, 47.5, pretty much bang on what we're expecting to see. Fantastic. Now all that's left is to wire up this battery management system, and as you can probably remember from the animation, we need to connect this to all the different individual cells so we can monitor them and keep them all in check. So that's why I added these little wires, so this easily accessible points for us to wire up this connector to feed all the different battery voltages into this.
This BMS also has a little temperature probe, so we can shove it next to a cell so that it can monitor the battery temperature.
Is it just me, or does this thing look dodgy with each iteration?
Oh god, is it the blue wire or the red wire?
First proper test. So we've got the battery temporarily hooked up to the bike. Let's see if we can actually spin this thing up. Yep, that works amazingly.
The JLC 3D printed case has arrived, and I'm pretty happy with how it's turned out. I've added some cutouts for a power port, charging port, on-off switch, and a battery percentage indicator. We're going to need a bunch of foam pads in the battery to help absorb any shocks and vibrations, because we don't really want the cells rattling around in there. The indicator is nice and simple, it just needs to be connected to the positive and the negative, and then it will guess the state of charge from the battery voltage. Right, let's get this thing finished. Finally, I think it's time to whack it on the bike and take it for a spin.
So I've run the battery down to about 50%, and so far I've done 18 kilometers, and that's without any pedaling really. So this is doing really well so far. Okay, we're fully out of battery now. Let's have a look. Yeah, completely dead. And we have done 33 kilometers. I'm really impressed with that actually.
And that's with essentially no pedaling. In pedal assist mode, I think we could easily get over 50 kilometers. The top speed I hit was 32 miles an hour. I could have gone faster, but I'd rather not on this dodgy bike. For a little cost breakdown, the 3D print filament, BMS and other parts used in the video totaled to around £60, which is about £200 cheaper than buying an equivalent sized e-bike battery. So there we have it. These disposable cells are actually really capable and valuable. Why the hell are they being thrown away after one use? Not only can we charge our electronics with them, but we've proved that we can actually use them for transport. I think this shows that we need to completely redefine what we class as waste and what companies can get away with. Since the start of this video, around 7,000 vapes have been thrown away in the UK alone, which is enough to build 53 e-bike batteries. So it really puts it all into perspective. So please give this video a share, like or comment, so we can spread as much awareness as possible. Luckily a ban has just been scheduled in the UK, but I guess we'll see how effective it is and how long it takes for other countries to catch on. So what do you think I should build next? I've managed to get my hands on about 1,000 cells, so I'm thinking of maybe making a power wall and actually powering a house. So subscribe if you want to see interesting stuff like that, and let me know in the comments what you think I should make next. Hopefully I'll have the open source power bank released soon.